Welcome back to EASD TV. Now for something really intriguing. I don't know about your country, but certainly in the UK, there's a complete obsession for cold water swimming. And everybody who goes cold water swimming, and they can be a bit of a bore if they do cold water swimming, but they will tell you that there are health benefits. Well, when I saw on the programme that there was something about cold exposure, I thought we have to have that for EASD TV. So please welcome three people who presented at that session. And we have Denis Blondin from Sherbrooke in Canada. Sorry, we're having to compete with some noise here. We have Tore Bengtsson from Stockholm University, and finally Lawrence Zach from McGill University in Canada. And I want you to notice that those are all very cold countries in winter, or at least I hope they're still cold in winter.
Yeah, we hope, yeah.
Okay, so Denis, start us off, just remind us what the body's physiological response is to cold.
Right, so generally when we're exposed to the cold, the first sort of response we get is that our blood vessels will try to vasoconstrict to keep our body from losing too much heat to the environment. But often that's sort of not sufficient, so then our body has to increase its ability to produce heat. It has to either recruit sort of muscles to shiver, or it'll recruit another type of tissue called brown fat to try to produce sufficient heat so that it doesn't, so we don't lose too much heat to the environment, or we can maintain our body temperature. So I think a lot of our interests are trying to understand what are these different mechanisms that we can recruit to try to help the body produce more heat to keep our body temperature level.
And why would we want to do that?
Well, good question. I mean, originally when we started in the area of cold exposure, the objective was more for to ensure we could improve survival or performance in a cold environment. We were looking at it sort of from military operations and trying to make sure that people could function properly and make proper decisions in a cold environment. Because if you're shivering a lot, it makes it really difficult to make good decisions and use proper judgment, and so it really impacts your ability to perform. And so at the time, we were trying to focus on how do we recruit certain mechanisms that'll keep us from shivering less, so that people can still produce the heat that they need, but without having those tremors. But in the process, we also learned that there might be some benefits to individuals who have a surplus of energy, like individuals who might have obesity or type 2 diabetes. By recruiting these mechanisms, we might be able to dissipate this excess energy that those sort of groups of individuals might have. So it was kind of incidental that we've discovered that there might be some benefits therapeutically for
I told you were going to be intrigued by this. It's really interesting, isn't it? So take us on from there.
Yeah, so what I'm interested in is actually to capitalize and utilize this mechanism, because when you actually get cold, you increase your glucose uptake in skeletal muscle and other tissues also. But the skeletal muscle is actually the biggest tissue in the body, and you can utilize a lot of glucose, and you can get a lot of stimulation of glucose uptake in skeletal muscle. And why is that good? It's because if you're type 2 diabetic, for example, then you want to push glucose from the blood into skeletal muscle. So what we have been doing, and what I'm interested in, is actually stimulating the receptor that is actually making this happen, which is the beta-2 adrenergic receptor, which is situated in the skeletal muscle. And what we have been able to do is actually find a new molecule that binds to the receptor in a novel way, so you don't get the side effects which we don't want to, which is problems with your heart and other problems. So we are actually tapping in onto this receptor, stimulating glucose uptake, and this is actually in a mechanism that is still working in type 2 diabetes, because in type 2 diabetes you have problems with insulin signaling and you're not pushing enough glucose into the skeletal muscle. But we are circumventing this with this natural pathway that is actually what you were talking about, Denis. So we have a completely novel mechanism here, and that's what I've been working with, and that's what I find very fascinating.
It is a fascinating and where does your research fit into this?
So my research is focused on brown adipose tissue.
So this is the brown fat.
The brown fat, and it's activated also by cold. And the conventional view in the field has been that it works through a protein called UCP1, uncoupling protein 1. But we find that not all of the benefits of cold can work through UCP1. There must be other factors that are involved. And so we study these UCP1 independent pathways of energy expenditure with the rationale saying if we're ever going to use brown fat for therapeutic gain, we need to understand all pathways that are involved in calorie burning. And so that's what we're focused on, UCP1 independent thermogenic pathways.
And if I remember, we start off with quite a lot of brown fat as babies.
That's right.
And then we lose that, so that adults don't have that much brown fat?
Yeah, they don't have as much relative to newborns. They don't have as much relative to small rodents, for example, but humans do have it. And so I think the biggest hurdles right now in the field therapeutically, and these guys can, correct me if I'm wrong, I think there's a mass issue, so there's people working on how to make more of it, but if we're going to make more of it, we also have to maximally activate it, and so we have to understand all the pathways that are involved.
And call me old-fashioned here, but you may not find a willing public when you say, I'd like to increase your brown fat mass. But just go back to the use of cold as a potential adjunct to therapy for people with type 2. I mean, clearly, and you hinted at it, a lot of people have comorbidities, particularly heart disease. And of course, you're really not wanting people with heart disease to jump straight into ice cold water. So what should we be advising people about cold water swimming, about turning the thermostat down and that kind of thing?
Yeah, I mean, I think these are some of the challenges we have at the moment where there's a lot of, it's quite common, especially in Nordic countries, to be doing cold water swimming. And we've seen a lot of research show the benefits of cold exposure. The problem is that when we're talking about cold exposure, we're not talking about cold water swimming often. The types of methods we use in the laboratory is not necessarily having people go into cold water because it's very difficult to control and there's other risks associated with it. So but ultimately, I think there's a lot of benefits that we see with the cold, even if you use cold water swimming. But I think there's some things that people have to be mindful of. I think there's a few reactions that you get, especially when you first jump into cold water. Often there's like a gasping reflex, so people will take a deep breath, and the risk sometimes is that people will asphyxiate on the water that they inhale.
And you get this diving reflex, don't you? From of old mammal, sea mammal days, where you go into cold water and you get this bradycardia and.
That's right, yeah. So when you just having your face covered in cold water is sufficient to drop your heart rate. And so you see these great effects. And so, but it also means that you have this conflict between your sympathetic nervous system that's saying, okay, you're exposed to the cold, we've got to ramp some of these mechanisms up that are going to help produce heat. And then you have your parasympathetic nervous system from having your face cold saying you can slow these things down. And for those who have who have a history of either heart conditions or a family history of heart conditions, that kind of conflict can be a bit of a problem. So that's why I think it's really important for people to ensure that they meet with their physicians first if they're going to do cold water swimming, to ensure that there are not any other underlying conditions that might put them at risk when they go into this somewhat stressful condition of having this conflict between your sympathetic and parasympathetic nervous system.
But on the other hand, you could turn your thermostat down by degrees gradually over a period of time and live at a colder temperature and also save yourself a lot of money.
And I think this is actually exactly the way. I mean, I was actually thrown into an ice wake when I was 10 years of my father, so I know the shock of that. But
have you ever got over it?
I came over it, but I think the important thing here is if you just turn down a little bit of the temperature, that could actually have quite of a dramatic effect in the physiology. So you don't need to jump into water, you just need to turn down the thermostat to some degree and not get too cold. But I think that's the thing. And that will actually also increase brown fat.
Sure.
So Lawrence, what are you thinking of this advice?
It makes sense. It makes sense to me.
So where do you think this field is going? Because it's very interesting. I mean, you're trying to develop a new molecule which kind of mimics the effect without having the concomitant dangers that there might be for people with type 2. But where else do you think we're going with this research?
I mean, I think on the cold side, I think we're trying to understand again what are these mechanisms that are so unique with cold exposure that give you these great therapeutic effects, and at the same time, we talk a lot about brown fat, and while it might not do a lot in terms of making sure that it's going to protect you from having a decrease in body temperature, it seems to have a very important role regionally. So protecting vital organs, where it's found, it's very specific areas that are close to our vital organs. So I think it's a matter of trying to understand how is brown fat contributing to protecting these organs, both from a thermoregulatory perspective, but also metabolically. And I think that's where some of these cycles that Lawrence works on is really important, because I think ultimately that tissue we know can take up a lot of energy and seems to be very protective of certain organs so that they're not overburdened with energy.
What can we learn from animals in this? You work on mice, but I'm very aware that at this time of the year there are all these fat bear contests. Who's seen the fattest bear in Canada before they go off for their hibernation? Well, it may not be cold enough for their hibernation, but can we learn something from other mammals about their use of fat in terms of cold exposure?
Definitely. I think there is a lot of research actually on hibernation, how you actually wake up from hibernation, that you need to turn up the heat, and that is actually brown fat driven. So I think there is a lot of research into this thermoregulation, how the body thermoregulates, that we should actually look into. Because I think one of the things that the type 2 diabetes has been very focused on is the insulin signaling. And insulin signaling is what is not working in type 2 diabetes. But there are a number of other signals as the sympathetic nervous system that actually regulate the body very, very much, and actually positively in this context. So I think there are a lot of things we can actually learn from this. And I think this has been a little bit overlooked in the field.
So just because you've got a broken indicator doesn't mean that you can't drive the car?
No, exactly.
And I think to add to that point too, I think, we know that even with individuals who have type 2 diabetes or pre-diabetes, while they might be resistant to insulin, their response, for example, their ability to clear glucose when they exercise is normal.
Exactly.
They don't lose that capacity. So they still maintain an ability to clear glucose, especially when there's a contraction involved. And so for us, we see shivering, it's just another type of contraction. It's a bit different than a contraction you get with exercise. It's like the context is somewhat different in that the muscles tend to use more glucose anyway. But I think it's a unique scenario that I think it shows here that it's still preserved in individuals with type 2 diabetes.
And Denis, I have to ask you before we close this, what have you found to help shivering Mounties do their jobs better?
Well, I think a few things. One is, I think from a performance perspective, definitely we see that the more you're exposed to the cold, the more your body can adapt to it and be more comfortable with it. And I think that's an important lesson to learn. If we're thinking about truly using cold as a therapeutic, I think it's important for people to keep in mind that, one, there's cultures that already do this. So it's not this sort of foreign thing that, you can adapt really quickly.
There's a place in Britain called Newcastle where they wear nothing all year round. They call a Newcastle overcoat is a spray tan.
Yeah, and I think, and then on the other hand, I think there's a lot to learn just from the mechanisms that are recruited. What makes these mechanisms so unique, and how can we tap into that through, either pharmacological approaches or if there's another way to figure out how these mechanisms are recruited.
It's fascinating stuff. Thank you so much for coming to talk to us about it. And I'll be turning the temperature down. Thank you so much.
Thank you.
Wasn't that interesting? We'll be back soon for more. Bye for now.